In this video, we're going to look at a couple of applications for first-order differential equations. These are going to be in the area that's called compartmental analysis, which involves a liquid flowing into a tank that contains another liquid. Stirring takes place, and then we have an outflow rate to be determined. So the picture of the model looks like this. So we have a known inflow rate, and we have an unknown outflow rate. We have a liquid initially in the tank, and we have a known quantity and a known concentration. And the model that we use to analyze this is, first we assume that x of t equals the concentration of the liquid in the tank, or of the pure substance in the tank at time t. So if we can find x of t, we solve the problem. What we do is set up a differential equation model that allows us to find x of t. And that differential equation looks like this: that the change in concentration of that pure substance x of t as a function of t is equal to the inflow rate minus the outflow rate. Remember from calculus 1 that rate is a derivative, right? So if we subtract the in derivative minus the out derivative, we should get the derivative of the substance in the tank, dx dt. To define inflow rate, we need to define inflow rate and outflow rate, so let's do that. So the inflow rate will be the flow rate in, which will be in units like liters per minute, times the concentration in, which could be something like kilograms per liter, or sometimes if it's a liquid, it would be like liters of substance per coming in per liters of substance in the tank. And so a flow rate in might be something like 6 liters per minute, and a concentration, let's say it's of salt, which we'll use in our first example, might be 0.1 kilograms per liter in the inflow. So what about the outflow rate? Well, the outflow rate has unknowns in it. The flow rate in will still be known, like 6 liters per minute, maybe 5 liters per minute. We'll actually do both those two examples. But the concentration would be the amount of pure substance in the tank, x of t, divided by the amount of liquid in the tank. So the concentration coming out requires that we know what x of t is, and because of that, that sets up the differential equations. The differential equation, remember, our model looks like this, and so the differential equation that we get looks like this: dx dt equals inflow minus outflow. And so let's look at this for a particular example. So we're assuming that a concentration of brine salty solution is flowing into the tank at 6 liters per minute, and the concentration of the brine is that there's 0.1 kilogram per liter 0.1 kilogram of salt for every liter that flows in. For the outflow, the flow rate that we're able to control in these problems is that we're letting the same amount out that was in, 6 liters per minute is coming out, but the concentration is whatever the amount of pure substance is in the tank divided by how much water in the tank. In this problem, we're assuming that we start with 1,000 liters of pure water, and so the amount of substance in the tank does not change, or the amount of fluid in the tank does not change since the flow rate in and the flow rate out are both the same. So the concentration out is that unknown amount of salt, x of t, divided by 1,000 liters of fluid in the tank. And this part right here, this concentration, is something that, concentration going out is something we always need to calculate. In the next problem, we'll see what happens if the flow rate out is different than the flow rate in, and then this denominator would not be the same as the initial amount. We need to change it by some function of t. So let's set up our equation, and it looks like this: dx dt, flow in 6 liters per minute, concentration in 0.1 kilograms per liter, minus outflow rate, the flow 6 liters per minute, and the concentration is x of t over 1,000 liters. So if we clean that up, simplify the numbers and the units, we get 0.6 kilograms per liter coming in, and we get 6 over 1,000 kilograms per liter, or 6 over 1,000 times x of t kilograms per liter going out. So everything is kilograms per liter, including the dx dt on the left side, so we don't need to write that unit anymore, so we can simplify our differential equation to this: dx dt equals 0.6 minus 6 over 1,000 x of t. So look at this differential equation for a minute and think about what type of differential equation it is. So let's hold it on the screen there for a minute. And do you notice that if we rewrite it like this, dx dt plus 6 over 1,000 x of t equals 0.6, it should be fairly clear at this point, I hope, that this would be a linear differential equation, with this being the p of t and this constant 0.6 being the q of t. So the integrating factor mu of t would be e to the integral of p of t dt. Since p of t is a constant, we can bring the constant outside of the integral and get just e to the 6 over 1,000 integral dt. Integral dt is, of course, t, so it's e to the 6t over 1,000 is our integrating factor. And we are solving this differential equation for x of t, right? So x of t is 1 over mu of t, which makes it e to the minus 6t over 1,000 times the integral of mu of t, q of t dt. The q of t is a constant 0.6. Let's bring that outside the integral, and then we're integrating e to the 6t over 1,000 dt, and then plus c. So it's a pretty easy integral to do, right? And we get this, right? We get, when we integrate e to the 6t over 1,000, we get e to the 6t over 1,000 back, divided by the derivative of that power. So we're dividing by 6 over 1,000, which is the same as multiplying by 1,000 over 6. And so we want to distribute distribute the e to the minus 6t over 1,000 across this bracket expression, and that gives us this. So it gives us, when we do this distribution here, and we get e to the minus 6t over 1,000 times e to the 6t over 1,000, which is e to the 0. So it's just the constant, and the constant is 1,000 over 6 times 0.6, which is the same as 0.1 times 1,000, which is 100, and then we distribute the e to the minus 60 over 1,000 times the c, and get c times e to the minus 6t over 1,000. So let's rewrite this on the next blackboard. What we have obtained, that x of t is 100 plus c e to the minus 6t over 1,000. Now remember that we assume that in the tank initially we had 1,000 liters of pure water, so the amount of salt, x of t, in the tank at time 0, x of 0 would be 0, right? So we can use that to solve for the constant c, and when we do that we just plug in 0 for t and 0 for x of t, so the left side is 0, and 0 equals 100 plus c e to the 0, right? So c equals minus 100, and we get this solution with c known. 100 minus 100 e to the minus 6t over 1,000. So suppose we want to know when does the concentration of salt in the tank equal 0.05 kilograms per liter. The concentration in the tank is the x of t divided by the amount of fluid in the tank, and so when the concentration is 0.05 kilograms per liter, that would be the same as when when x of t over 1,000 equals 0.05 kilograms per liter. So if we solve that for x of t, we see that x of t equals 50 kilograms, right? If we cancel out the units, and so if we go on to the next blackboard to solve for what time the concentration will equal 0.05 kilograms per liter, we just solve for x of t would be 50 equals 100 minus 100 e to the minus 6t over 1,000. We need to solve that for t, and so let's move this term over to the left side and move this term over to the right side to get 100 e to the minus 6t over 1,000 equals, we move the 50 over and subtract it from the 100 and get this, divide through by 100 to get this, e to the minus 6t over 1,000 equals 1/2. Then what do we do to both sides to get the power down, right? We take the ln of both sides of this equation. And remember, when we divided by 100, that should have given us a half on the right side. So we take ln on both sides, that brings the power down, that gives us minus 6t over 1,000 equals ln 1/2, which is minus 0.693, and if you go through the calculations, multiplying by 1,000 and dividing by minus 6, you get that is 115 minutes. It takes 115 minutes for the concentration of salt in the tank to increase, right? Because it started off pure water. It takes 115 minutes for that concentration to get to 0.05 kilograms per liter. Okay, so that solves this first problem where the remember if we go back, the inflow rate and the outflow rate were both 6 liters per minute. Let's take a look at another example where the outflow rate is different than the inflow rate. Let's make the outflow rate 5 liters per minute, but leave everything else the same. So I've got almost everything written in here. The inflow 6 liters per minute, concentration 0.1 kilogram per liter. The outflow is different than before. It's 5 liters per minute out. Now, remember the initial amount of fluid was 1,000 liters, but in every minute we add a liter of fluid because we have 6 liters coming in and only 5 liters going out. So after 1 minute, 1 liter we add. After 2 minutes, 2 liters we add. After t minutes, right, we add how many liters plus t, right? And so our differential equation looks like, or setup for the differential equation that we're going to solve looks like this. Inflow 6 liters per minute, concentration 0.1 kilograms per liter, same as before, but this part is now 5 liters per minute times x of t over 1,000 plus t. Is it still linear? Well, let's take a look at it in its form like this. Moving both x terms over, we get 5 over 1,000 plus t times x of t equals still 0.6. Yes, it is still linear, right? This would be our p of t, and this is our q of t, and our integrating factor takes a little bit more work to figure out. Mu of t is e to the integral of p of t dt, and that is what bring the constant out. Dt over 1,000 plus t, is that not ln of the 1,000 plus t? So it would be what, e to the 5 times ln of the denominator, and we don't need absolute values because 1,000 plus t is always positive. We bring the power up, e to the ln of 1,000 plus t to the 5th power, and then the e and the ln undo each other, and so our integrating factor is 1,000 plus t raised to the 5th power. So we'll finish this on the next blackboard, but remember x of t is going to be what, 1 over mu of t bracket integral mu of t q of t dt plus c. And so what does that give us? X of t, 1 over mu of t, just changes the power to negative, so that's 1,000 plus t to the minus 5th power. The q of t is 0.6, a constant, and then we're integrating 1,000 plus t to the 5th dt plus c, and we're going to distribute the integrating factor 1,000 plus t across that bracket once we integrate. So let's do the integration step. So we get, just leave this expression out front of the brackets for now. When we integrate 1,000 plus t to the 5th, that's just like integrating u to the 5th, right? Because du would be dt, so isn't that 1,000 plus t to the 6th over 6? Put the q of t back out front, put the plus c back in. Now we're able to distribute this expression across the bracket. When we multiply 1,000 plus t to the minus 5th times 1,000 plus t to the 6th, we get 1,000 plus t to the 1st, or just 1,000 plus t, and when we resolve the constants, 0.6 over 6 is just 0.1, and then we distribute the 1,000 plus t to the minus 5th across the c and get c times 1,000 plus t to the minus 5th power. So that's our x of t. That's our solution with the c not yet known. On the next blackboard, let's solve for c. So we had what, x of t equaled 0.1 1000 plus t plus c times 1000 plus t to the minus 5th power. X of 0 was 0. Plug in 0 for t and 0 for x of t, so 0 equals 0.1 times 1000 plus 0 plus c times 1000 plus 0 to the minus 5th. This number right here is 100. So we bring it over here, we get minus 100 equals c divided by 1000 to the 5th, or c equals minus 100 times 1000 to the 5th. Turns out to be a little bit nicer if we rewrite that like this as minus 0.1 times 1000. 0.1 times 1000 is another way to write 100, and then it's 1000 to the times 1000 to the 5th. So that's the same as minus 0.1 times 1000 to the 6th. So let's so I've written that down here on the bottom of the board, plugging in 4c, the 0.1 times 1000 to the 6th power. So here's our solution for x of t with the constant c plugged in. Now, can we do the same thing that we wanted to do on the last problem? When does the concentration equal concentration of pure substance in the tank equal 0.05 kilograms per liter? Remember, the concentration in the tank, last time it was x of t over 1000. This time, remember, the amount of fluid in the tank is not 1000 at any time t after the start of the problem, it's 1000 plus t. So that tells us that x of t is 0.05 multiplied by 1000 plus t. And so we're going to plug this in and solve for t. So on the left side of our equation here, we're going to make 0.05 times 1000 plus t. The left side of the differential equation is not 0.05, it's the concentration that's 0.05, and we have to solve for x of t as we just did. And then what were the other terms? 0.1 times 1000 plus t, and then minus 0.1 1000 to the 6th, and 1000 plus t to the minus 5th, right? And so this could be a very difficult problem to solve with powers of t throughout spread across 3 different terms, but it turns out that each time t appears, it appears as 1000 plus t, albeit to different powers, so we can divide through by 1000 plus t. So we're going to divide every term on both sides by 1000 plus t, and that simplifies things quite a bit. 0.05 equals 0.1 minus 0.1 1000 to the 6th power, and it puts the unknown t only into this one term, 1000 plus t. We divided it by 1000 plus t, so now it becomes to the minus 6th power. Let's move this term right here over to the left side and move this term right here over to the right side to get this 1,000 to the sixth. Instead of writing 1,000 plus t to the minus 6, let's write it as 1,000 plus t to the sixth in the denominator. We're moving this 0.5 over, subtracting it from 0.1 to get 0.05. Let's multiply by the expression involving t, this expression here, and divide by 0.05, and that gives us what? That gives us this. I had forgotten the 0.1 right here. And we were going to take, to solve this, take 6 roots of both sides, right? Take 6 roots of both sides, and when we do that, we get, what, 1,000 plus t on the right side, and on this left side, the 6th root of 1,000 to the 6th is just 1,000. This number right here, 0.1 over 0.05, is 2, and we're taking the 6th root of both sides, so it's the 6th root of 2, which is approximately 1.12, and I'm sorry, 1.122. So that is approximately 1.122. Multiply that, and we're multiplying that by 1,000. So that gives us what? 1,122 equals 1,000 plus t. And when we solve that for t, we get 112 minutes. Remember, before we got 115 minutes. We're building up the concentration of salt in the tank. In this case, we are going to build up the concentration of salt in the tank just a little bit faster because more salt is coming in to make the tank a little bit more briny because we're letting some water out. And so we see these two examples. Let's look at the model and the DEs just one more time on these. So our model in all cases is the simple model dx dt equals inflow rate minus outflow rate. In the first case, that gave us dx dt was 0.6 times 0.6 minus 6 over 1,000 x of t, and as a differential equation, once we put it into the form where we solved it into the linear form, we got this differential equation right here. If we compare that to the differential equation we get in the case when the outflow rate is less than the inflow rate, it just makes a change to this denominator part, and let's look at that. Right, it's very similar differential equation. It still has the 0.6 on the right hand side, still has the dx of t plus, but the only difference is that that denominator, instead of being 1,000 plus t, is just 1,000. And we did get fairly different solutions in these cases. In the first case, x of t looked like this, and in the second case, with the different outflow rate, we had a more complex solution. It wasn't a hard differential equation to solve, but when you put in all the constants, it looks more complex. And when we were solving for the unknown t, that made it a little bit more complex in this second example than in the first. One more thing on this second example, or actually on both examples, when we're given that concentration, we need to make that we're trying to find at some future time t. We need to make sure that we set that equal to the concentration. That given concentration is not x of t, it's x of t divided by the amount of fluid in the tank. So in this second example, that was x of t over 1,000 plus T that was 0.05 kilograms per liter. And in the first example, we set 0.05 kilograms per liter equal to not X of T, but X of T over the amount of fluid in the tank, which was 1,000 liters. So this concludes this video on section 3.2, compartmental analysis. We will only be doing inflow and outflow type problems in this section. We won't be doing the other types of problems that you find in your book in this section.